So I'm going to talk about React and why it's still something we use in 2021. Just to start and to set the ground, I believe React is a really good piece of software. But it has been around for 8 years now. Recently, it had its 8-year birthday, which in development times is ancient. It could be strange if it outlives jQuery, which, I mean, it's quite possible at this point. It's not like nothing has happened in the web ecosystem in those 8 years, but it doesn't feel super alive. Things have happened though. We had TypeScript now, we have concurrent mode coming to React, and there has been a lot of improvements in JavaScript. But if you share my perception, what we have been doing with React is with JavaScript, with the web, is mostly pruning around the edges of the garden, picking the low-hanging fruit, reaping the benefits of the things that we sowed a long time ago. Maybe the next big thing will be WASM. Maybe we will have a completely different landscape in any time now, or maybe there will be some other new shiny thing, or maybe we will be looking at React at the end of times. Who knows? That's not my game here. I don't want to try to prophesize what's going to come. Instead, I want to talk about what I believe that React did well. And in particular, what I think that React does just right. So yeah, this talk is about fractal growth. I'm going to explain what that is in case it's not, we're not familiar with the idea, and how I believe that's a key reason why components rule. So when I say fractal, if you're familiar with them, this image might come to mind. This is the Mandelbrot set, which is the product of executing a certain mathematical function recursively in the complex plane. You end up with this shape. Very pretty. One thing that characterizes it, and many people find often, is that as you zoom into the shape, which has infinite detail, by the way, you find these islands of what looks like to be the same shape, again, smaller inside. Very interesting, but this is not the kind of fractals I want to talk about. The kind of fractals I want to talk about are more like this. This is a branch on a pine tree somewhere around here. In the left, the first quarter of the image is the end of the branch, which splits into two, and then those turn into these needle leaves that the pine trees have. Then in the second image, coming from the left, you have the same branch a bit further up, a bit older split, where the pine tree split before, and then in the third image, before that, and closer to the trunk. So we have a similarity happening in the way that the shape is being expressed. We find that also in ferns, again. What's interesting about these ferns and contrasted with the pine tree is that it gives us even more detail into the process happening. You can see how the tip of the fern looks exactly like one of the leaves inside the branch, the older part of the branch. And really, you can see that this process is literally what's happening is that tip is breaking apart into many subleaves, because one of the subleaves of this branch is already making its own subleaves. Now, when we think about plants and trees, we think about objects in the same way that we think about houses or cars. But that's really because we live too fast. If we can think more of them as processes, they are like waterfalls frozen in time. What they really are, the plants, is processes. A tree is really just the process of growing a tree. It's embedded into its shape. The way that it deploys itself is by growing onto itself. Its mechanism of growth is the same thing as its shape. That's very different than a house, which you build once, and then you end up with a house. You have to maintain it, but you're no longer growing it. So this is all very abstract, and we're going to be touching a lot of abstract subjects on fractals and so on. So to ground it a bit and to see how this is actually related to the code and can actually be meaningful in the day-to-day, we're going to follow a tiny refactoring exercise. We start with this field component API that looks like in the left, which if you find it the same way as me, you find that the right version, refactored, looks better and is a better implementation. Now, I don't want to just suggest my personal view on how API should look like. I want to find a maybe objective metric by which we can measure that this is a better API. So we're going to be walking through this exercise. But ultimately, my contention is that software systems can be better thought of as ecosystems than as buildings. That's why I'm introducing the idea of fractal growth from plants. And I want to try to demonstrate this point and illustrate how using the right metaphor can actually help you understand the problems that you're trying to solve, because the constraints may be fundamentally different. So let's go a bit into the code. We can look at this field. It has maybe too much information. This is what it wants to represent, right? It has a value, some icons, maybe a pop-up. But let's take a step back and think about a simplified version of this field. So this one has a value and a placeholder and a handler for onChange, almost as simple as a field can be. But how simple is it? So one way we can think about how simple a component is to think about what would it take to test it completely. So we can think of variations that we would like to test. If we're writing documentation for this field, we might want to illustrate these 4 variations, which is that you have a placeholder and no value, or that you have a value, or that you don't have either placeholder or value. Or if you want to stress test it, what happens if you put a really long value into it? Well, this is one way in which we can measure it, but we can formalize it even more. We can think about the variations for each of these props that we want to take. So for the value prop, we might think that we want to test what happens if you send an empty string, what happens if you send some value, and what happens if you send a really long value, which ends up with being 3 variants. Then for the placeholder, it could be empty or it could have some value, right? Of course, we can test many, many more. These are strings, so the amount you can test is infinite. But let's stick with what we think could actually make a significant impact in the result, right? As the behavior will change. Finally, for the handler, if we are thinking about the testing in the documentation, we probably don't care too much about what the handler will do. So we just want to put in the API that there is a handler. This will not lead to any extra variations. Now we can plot this into a matrix in which we have the several variants for the value and the several variants for the placeholder. And with that, we can represent what the states are going to end up being. And because we had 2 placeholder values and 3 value values, we end up with 6 variants in total. Again, the handler is only 1, so in that case, it will not multiply to anything more than 6 in total. Sorry, I cannot read the messages right now. I'm going to check that after I'm done. I saw a window pop up. And so we have 6 total against the 4 that we had when we wrote this manually. And you might think that these 2 examples right here, which are they are saying the same value as the ones above. So the placeholder existing or not in these 2 examples doesn't really make an impact. So is it reasonable to think that these add complexity? Is it reasonable to think that we should test this? Well, I mean, what I invite you to think what will happen if when you render them, this is what you see instead. So that would actually be a bug. And this is a situation in which we can end up by filling those properties if the implementation is buggy. So it is meaningful to test them, even though if everything goes well, they will look the same as the other examples. Another property this field had was a label. So let's add it back, and let's see how adding a label impacts our total of complexity. So as we add a label, we can add an empty label as a variant, a short label as a variant, or a really long one to see if we should fold it into many lines or truncate it and add an ellipsis. And that brings our total to 18 variants now. We can add the tooltip back. Now, the tooltip is 2 properties and a handler. We can ignore the handler for now. When we add those 2 properties, we might want to test what happens if they have a short value, a long value for the tooltip, but also because the tooltip might not be there, we make it optional. We also want to test what happens if it's null. And then for the tooltip position, we want to test valid positions like above and below, but because it might happen, we also want to test wrong value, empty, and of course null in case there is no tooltip. Now notice there is something strange here, because would you have a tooltip position if you don't have a tooltip? That makes no sense. But in this API, that is perfectly possible thing that you can have. When you add all of the variations up, multiply them actually, you end up with 360 variants, which, yeah, it's growing quite fast. Now we are going to add the icon next. And if I'm correct, yes. When you look about the API of the entire thing now that we added back all the properties, we could represent this API in a different way. What if we were to think about the component itself as a branch and about the properties that it has as leaves? I mean, you can think of a React tree as, well, a graph, where the components are the nodes and the terminal things that cannot be expanded further, which are the props, they are leaves. So we can represent it a bit like this. Now, when it comes to plant comparisons, here's a different fern. This one is simpler. This doesn't have that parts that the branches that grow up of this main branch, they don't subdivide further. So this is more into the lettuce territory. Which is more what we have here. It's like there is one root, and then all that comes out as leaves. They are not branches, they're just leaves. So what's my point with that? Well, that's as tall as this fern grows. It cannot grow further than that, because the structure is just too simple. There is no possibility of adding that extra complexity in that structure. So it kind of collapses on itself. Now, when we add the icon properties into the grand total, we end up with 10,800 variants, which is, well, a lot. Let's imagine that we're not just dealing with a field, we're dealing with the entire application. And going back to the tree metaphor, let's imagine that we're trying to build a tree. Now, if we are thinking combinatorially like this, we might want to have a way to represent every tree in the forest. And if you're thinking about the possibility of representing everything in the forest, and you want to codify that, and I know this is absurd, but I want to illustrate the point of how approaches eventually fail. If you would have to put that into the DNA of a tree, every possible variation that it has to adapt to, every possible environment that it ends up in, you would end up with a number that is just impossible to imagine. Like, combinatorics is a crazy part of mathematics. You can easily get into numbers that are larger than the amount of particles in the universe. You saw how fast this was growing. Of course, that's not what the tree does. That's not how it solves that problem. Instead, it just has a way to grow a branch, which produces leaves, and from that branch, it recursively creates other branches. So we have the problem of combinatorial explosion, and we see that the solution taken in nature of that is this fractal growth inside each other. This will lead us to two different types of modularity. Let's go back to software development, but now not thinking about React specifically or about a use case, but in general how a software development ecosystem evolves over time. We can think of software into layers, like every piece of software I built into previous pieces of software. That happens even within our own application, within our own systems. And we do call that, when it's in our own application, we call that legacy. We don't like to work with that. But technically, every piece of software that is already extant out there is legacy. So when we find software growing by accumulation and in a kind of disorganized manner, we can find different types of analogy with the natural world. This, I find it very interesting. There is this type of mold that grows. It's a single cell, like it's not many cells that grow differently. It spreads over a surface so that to maximize the connection between points of nutrition. So what some researchers decided to do is to make like a map of the area of Tokyo in Japan, to put pieces of oat, which is a food that the slime mold really likes, distributed like the population centers in that area, and then let the mold grow. And the shape it created is remarkably similar to the rail system in the metro area of Tokyo. Now, that rail system was designed by engineers over a long period of time and with a lot of expertise. So people use this sometimes to say, oh, this slime mold might be really, really smart. I think this makes a different point altogether. I think the point it makes is that at some level, the systems grow so complex that we can no longer have the ability to plan ahead. And instead, things grow by themselves in this organic fashion. And again, there is my claim that software systems are better thought as ecosystems than as buildings. Nothing as fixed and pre-planned as architecture can really reflect a process like this. I think specifically when we talk about modules in the software system environment, we are actually talking about two kinds of modules, and we mix them together. We don't differentiate between the two. Going back to the code, we had this problem that the structure of this field might be, well, on the one hand, too complex because the combination that you can get to test this are just unwieldy. It's just too many. But on the other hand, it's too little structure. We know from the Fern example that it's not the way to grow further. But we have pieces of functionality grouped within these props. We have the tooltip, which really, it's a thing on itself. We can think of the tooltip as a separate thing than the field. So how about we extract that? So let's separate this code into two and move out the tooltip properties into a sub-component of the field. Now, the benefits of this can be already apparent. One of them is that we can drop those annoying namespaces. We don't have to call it tooltip position because now it's namespace automatically by being inside the component. It's the position of the tooltip, obviously. The onClosed also doesn't have to be on tooltip closed. So we have some cleaning in there, and that's nice. It looks nice in my opinion. We also have now the ability to set the text instead of just as a string for this tooltip. Now it's React children. So you can pass formatting into it. You can put links into it. You can put images. So it's not just that we namespace it in some way. We also isolated. We also added extra possibilities. When it comes to the complexity of the tooltip, well, if we compare to the circumstances we had before, just by taking the field tooltip in isolation and using the same amount of variance that we had before for the props, we get 20 props in total, which is, yeah, it's fine. We can deal with that. But actually, we can do even better. Because now the field tooltip is isolated, we can hide the field tooltip as a whole. So we don't need to support nullable children and position. So we can eliminate the null variant when testing this one, and that actually brings the total to 12 variants instead of 20. So we're getting in there. When we plot this into our tree view, we can actually see some more structure. The field tooltip is no longer just a series of props. Now it's a different node, it's a different branch, which has its own leaves. And the children of that field tooltip are an even deeper branch. So we can already see that hint of recursion. Going back to the code, the next thing that we can extract is the icon, which also makes sense to make into its own component because those two properties, the type and the position, are very related to each other. And when we take them in isolation, again, the amount that we're going to have is less, but because we have a component for these properties, we can strike out the nullability of them. We don't need to nullify them. If you don't want an icon, you just don't put a component for field icon. We can make them mandatory and bring the total lower to 20. Now, you look at this example and you can see, well, we still test an empty position and a wrong value, which is not exactly ideal. Well, yeah, we can bring this number down, and we will, but we'll come back to that later. For now, let's just move things around. This is how plotting this new tree looks like, right? So we're getting somewhere. Now let's talk about the module types that I was referring to. And I'm going to call these two module types combinatorial and fractal. Now, these are my names for them. There are infinite names for them, as many as, well, people talking about them. But they follow into understandable categories that can be related to some technical mathematical concepts. I'm going to mention those. So the first ones to talk about are the combinatorial modules. And this is this sort of modules. So you can think of a brick as a module that you can combine, well, side by side with other bricks or on top of each other, and out of that you make a wall. And then you can combine a couple of walls next to each other, and out of that you make a building. So that's the first characteristic of a combinatorial module. It combines side by side. See how props in a single component are one next to each other. They are not, they are one next to each other. So that's the first characteristic. The second one is that when you put modules that are combinatorial next to each other, the total grows in a predictable way. What do I mean by that? Well, if you make a wall out of 2 bricks, the wall will weight exactly the 2 times a brick. Now, these relationships in some combinatorial modules don't have to be so simple. They could be multiplication of the other one. It doesn't have to be like exactly for each brick is 2 times is. It doesn't have to be so simple in any way. But in mathematics, this is what we will call linearity. This I'm just mentioning the technical word to relate it to something that can be Googled for afterwards if you're interested in this kind of thing. The last thing that we can observe about the combinatorial modules is that the wall does not look very much like a brick. So when you put many bricks together, what you end up with is not just a larger brick. It doesn't grow that well. The brick is a 3-dimensional shape. The wall is kind of mostly 2-dimensional, and the house is again 3-dimensional and it has holes. So they're very different things. And when we can think about this as that when you zoom out, a combinatorial module like put next to each other end up looking different, having different shapes. Let's talk about fractal modules next to compare them with. We had this illustration from before. And the first thing that we can see is that branches grow out of branches. This is fundamentally different from putting bricks next to each other. The first characteristic then is that a branch grows out of another branch. Fractal modules nest inside each other. They don't go side by side. Another characteristic is that if you say that the tree is made of 2 branches, what is the weight of that tree? Well, it depends. Are those 2 branches growing out of each other? Are they the same size? Actually, we cannot know in general. We're going to go deeper into this, but this is one of the problems of fractal modularity. It's not easy to know how a growth in the amount of modules inside the system will impact the total shape, the total size of it. But another very obvious characteristic is that as you zoom out, you have some structure that still remains. This small branch looking like larger branch, of course. It doesn't have to look exactly the same. But we call this scaling variance, again, the technical term for it. And this is the easiest way, more intuitive way to find if a system is a fractal in nature. You can recognize it very easily by looking at that. Now, just to recap, side by side, combinatorial modules will compose side by side. Fractal modules will compose inside each other by nesting. Combinatorial modules grow in a predictable fashion. You can actually write equations for that, while fractal modules, not so much. In combinatorial modules, the whole looks different than the part. The modules do not have the same shape as the total form thing they compose to. Fractal modules are scale invariant, not always, but typically. So you will find the same shape when you zoom out. Now, why is this important? Well, it's because fractal modules are a far more general solution to really any sort of problem that you might find. Like they adapt to more problems. They actually model more problems in mathematics. That's why you find them everywhere in nature. The problem is that they are literally chaotic. Again, this is a technical term, and we can go into what that means. You might be familiar with this. It's a very common example of the pendulum that has a pendulum attached to it, double pendulum. This is an example of a system where the previous state of the system is part of the input that allows you to calculate what the next step is going to be. And what happens with a system like this is that a small notch in the starting position leads to wildly divergent trajectories very fast, which leads to unpredictability. Another classic example is the three-body problem. These are three masses in three-dimensional space that attract gravitationally each other. And if they are roughly the same weight, so to speak, if they are roughly of the same mass, we have a really, really hard time predicting how their evolution is going to be. But in reality, it's even worse, because those that I just mentioned, they are toy models. They are mathematical models that we have equations for, and we can have as good data as we want. In nature, we don't have that at all. So we need to also account for the fact that we don't have the equations to model the processes, and we don't have nearly enough data. And this is a good point as any to mention that what is typically understood as a fractal is not exactly what a fractal is, but more importantly, it's not the most useful definition of a fractal. The focus of fractals as a concept is in roughness, in the fact that in this unpredictability, in this complexity of the systems. This video by Tree Blue and Brown on YouTube is excellent. So if you're interested in this topic, I highly recommend going into it. It really opened my mind about this topic. Going back, combinatorial modules are what we call linear systems, which implies all of this predictability. And fractal modules, well, not so much. Now, how bad is this? Let me give you an illustration of how problematic the complexity of a fractal system can become. We said that combinatorial growth, combinatorial explosion, can go into gigantic numbers very, very fast. But if I tell you that I have 60 variants of a particular component, we are currently testing 10, and we say that we're going to test 3 times more, then we are testing 30, which is a decent chunk of the 60 variants, which is 30 is 3 times as much as 10. So we have a coverage that is 3 times higher. There is some proportionality between our level of effort and our outcome. Now consider this slide looks empty, but it's actually this very same image blurred into irrecognizability. Now this image has a lot of detail, and we could say roughly, it is very rough, but let's say this image has 1 million more pieces of information than this other one. Well, if we were to make an effort to improve our capacity of measuring by 1 million, how much do you think our predictability horizon, which is how much we can predict about the evolution of the system, is going to be? Now, if we start with one data point, like here, and we increase that amount of data by 1 million, if for one data point we had 1 day of predictability horizon, by one calculation, the next predictability horizon we're going to have after 1 million data points is 3 days, which is brutal. And if you think back about my claim that software systems are thought as ecosystems, which are chaotic, rather than as buildings, if you ever sat in a planning meeting thinking about what to do in the next months and you had the feeling that it was pointless, well, what can I say? So about that calculation in particular also, it's illustrated very well in this video. If you're interested more in finding about how chaotic systems are described mathematically and how all of these things are calculated, I can highly recommend looking at that one as well. It goes into the details of how actually that ratio is calculated. So we said that combinatorial modules are terrible because they adapt to immense number of variations, and fractal modules are terrible because they lead into chaos. So how do we deal with this? How do we manage the trade-off between the two? How do we choose them? And I suggest that we also take lessons for ecology on that. What constrains an ecosystem is the availability of energy. So it needs to choose which of the two modules is the more optimal for the energy at the particular problem that it has to solve. This is entirely the same as us. It's usually that in our case, energy is mostly money. We need to make good use of the money. So you will find typically, and this is just a trend, it's not a rule, that at the smaller scale, things tend to be what I would call consistent, which is combinatorial modules. They are discrete pieces that mount side by side, and they look more or less the same. And you can predict more or less what shape and contents they're going to have. You can actually do this with really tiny organisms that we even know how many cells they have in their bodies. But as things grow and become more unmanageable, then you go into fractal. You go into fractal modularity, which is what I would call globally complete, which means that at the larger scale, it can adapt to whatever you throw at it. But at the price that you might not know what that is. You cannot plan that in advance. So if we go back to the example of what's happening here, the slide mold does not have the advantage of seeing where these odd pieces are placed. We can see that and we can try to plot a map over it, but the slide mold does not have any perception like that. So how does it do this? It adapts reactively to it, right? And this is what I would call reactive awareness, which is that as you find an opportunity, you move further into a direction. If you find that the opportunity is no longer there, you can prune. You can prune the branches of a tree. That's why trees typically throw part of themselves that are no longer useful. And you can see this tree flowing into the sunlight, finding that as the optimal space. This, I would argue, is a form of perception. Now, you can sympathize with this tree and with the slime mold because something that we don't know is how every piece of the software ecosystem is evolving right now. We don't know what the users are going to need tomorrow. We don't know what the company priorities are going to be. We don't know if a pandemic might happen. There are many things we don't know. And at some level of scale, we need to stop predicting and adapting in this manner. And that is the value of a component. This is what React components allows us to do, as contrasted with other types of module that compose in a more linear manner. So the trade-off that we have to live always with is the development cost, which includes our cognitive load, and this componentization allows us to deal with smaller pieces that we can comprehend readily. The testing cost, which really means that we need to reduce that combinatorial explosion to something manageable, or the corner cases will eat us alive. And the runtime cost, which is how the application actually performs out there. And if that cost is too high, if the performance is too slow, if it takes too much to run our app, it will lead to user attrition, which leads to less money for the other two priorities. Components, however, are not, and just to clarify, I'm not saying that components are really the only solution there is out there. They are actually suboptimal for very simple tasks because they have a computational and memory overhead. You need to do extra processing because you have components, which is the famous abstraction cost. There are tasks that are so simple that don't need this. And of course, they introduce this fractality, this chaos that makes a different type of unpredictability. Now, I mentioned before that we could improve this API even a tiny bit further. And so let's do that now. We said that the field tooltip has 12 variants now coming out of these 3 variants for the children and 4 for the position. But really, we are being excessively unrestrictive in the position by using a string. Because it allows the developer to pass any sort of values, which is not something we want. So something we could do is to make sure that only we allow the above and below valid values to be passed into position. There are many, many ways of doing that. And one that I could mention just as an example is to use symbols. I mean, they're pretty nice because then you cannot accidentally make a string that looks like one. And if you're using TypeScript, you can actually type for them. So now we can be confident that nothing that is not these above or below values can be passed into this prop. We can draw that here into the code by putting it in orange like that. And then when we calculate this again, which is only 2 variations for the position, we end up with only 6 variants when before we had 12. So we can go even further in this reduction of the complexity by doing nicer APIs by being more specific with arrow types. When we plot this into the tree view, I like this because if I put it orange because it's a different type, it looks like it has a flower or a fruit, which is kind of neat. And we can do the same for the icon, of course. The icon has a position which can only be left and right in the field, and a type which can be many options, but they are discrete and there are only some, so we can also make them into some sort of enum. And then we go back down from 20 variants into just 6, which is, again, quite an improvement. And this is to show that there is value in types for the complexity management on this level as well. Then again, when we plot it as a tree, we also get it pretty like that. And just to mention a disclaimer, because I'm talking about reducing the combinatorial explosion, there is something we're hiding here by creating these isolated subcomponents. We are only testing each piece in isolation. But because we are allowing for recursion, theoretically, somebody could keep adding and adding children and children nested inside each other. And that's where we end up with all the chaos things that I mentioned before. But we need to make a trade-off, right? And the trade-off we can find in this particular example, we may find that we like these smaller subcomponents that we can control. We can think of them in isolation within a reasonable level amount of variance. And, well, we open this other door, but hopefully that's not something that will actually happen. This is then how the finished API looks. Now, I have defended why React becomes a very, very useful tool for modeling the real world problems. And I asserted that we can control the combinatorial explosion by using these component APIs. But I'm also mentioned a lot about this variance that the component can have and how useful it is to think about those variants as something that we could potentially test. So is that something we could actually do? Now that we know that we don't have to test 10,800 variants to test a field, that we could do it in a more isolated, controlled manner, could we take advantage of this thinking, combinatorial thinking, for automated testing? So if we were to do that with the icon, and we have 16 icons, let's say, and they can be in like a default or disabled state, then we end up with 32 variants total, which, I mean, is a number, but we started with 20 variants being added to the field only to test some part of that icon, and in mostly invalid cases. So going to 32 variants for a complete coverage of the icon is not bad. For the tooltip, we could do the same. Again, we are not testing every potential use case ever, but we're testing all the ones that we find meaningful and just generating all the variations of that. And we could do the same for everything. Now, once we test the isolated pieces by themselves, then we don't need to test all those sub-variations when we compose them together. So we could imagine having a testing suite that looks a bit like this. It's just a page that you can scroll that auto-generates all the variations. And we could imagine these screenshots are taken automatically, and when you do a change, you can run it again, and it will show you a difference when it finds it. In my point of view, robust regression testing should have a really good performance. It should have a very decent usability that is pleasant, so that we actually do regression testing all the time, and that have a wide coverage, that it covers as much examples as possible. And I think that if you have used snapshots in Jest, they cover this quite well, although they are not auto-generated, so you don't have all of this extra corner case coverage. But if we think about this in screenshot testing, this could be doubly good. So yeah, this is something that I propose as a potential way forward. I know that this is possible because we did it in some teams that I work with. And it depends, but it relies heavily on all that I mentioned before about this thinking of doing these modules at the right scale, and then trying to make them combinatorially complete, but only in tiny scales. And so let's reach the conclusion. Why are we still using React in 2021? Hopefully by this point is obvious what my argument is. That components give the right amount of surface for us to test and think about, and allow to nest inside each other recursively. So they allow for fractal growth, when the other type of modules is not useful enough. And really just a damn fine piece of software. My other point that I hope I illustrated to some extent is that we can take lessons from completely different disciplines that I took from ecology and chaos theory in this case, but many other allegorical thinking can help us in illuminating our understanding, and that doing so hopefully improves our ability to apply those patterns in the code in the day-to-day. Thank you very much.
Good stuff. That was very interesting. Thank you for that. So yeah, if anyone has any questions, feel free to post them as in the chat, or simply raise your hand and turn on your mic and we can do it. Perhaps everyone is mind blown and don't have anything. We'll see. So one thing I was wondering is, could you tell us a little bit more about like how you apply this in your various different teams? Was it you applied it through design systems, etc.? I would imagine.
Yes, and that is quite the motivation also. In a design system is particularly meaningful to try to get all of them covered, because some people will use things in the way that you didn't expect, or a use case that you just didn't imagine at all. So we had the motivation to have this kind of combinatorial testing, and we built some tools for making that possible. The lesson really was that to try to keep the combinations controlled. And we found so many benefits of that, so that motivated all of this.
Mm-hmm. That's very cool. So let's see. So we have some questions here. I think, what do you think, Mr. Jack Edward? Nice work. What do you think about using state machines to generate permutations for testing? For instance, model-based testing.
Yes, so that could be the next logical level. And yeah, I haven't done that. That's super interesting. Reason I haven't gone into that yet practically, I haven't tried that, is because we mostly tried things that just render something. We haven't tried testing behaviors in this manner. But yeah, that's a really good point. I think that could work, and I think that it could require some specific thinking to the actual like transitioning through states. So again, it doesn't explode in size far too much. But I think that would be a very, very powerful thing to have.
Cool. And yeah, Victor Linder asks, do you have links to the YouTube videos?
Yes, I'm wondering where to post them. I don't have them right at hand, and in the chat they're going to get lost. So I think I can post them somewhere else.
Send them to me, and I'll place them on the meetup page as well as a comment there.
Awesome.
So Jack is writing some more here. This is also a super powerful pattern when you combine it with the use of context, implicit wiring, and compound components. Love this.
We actually did that as well. So yes. So as you can imagine from that field example, there might be states of the field that are meaningful for the children of the field. So I didn't demonstrate that, but if you have the state in the field in a wrong error state, you want the icon to show that as well. You want the icon to be read as well. So you want to set the context at the level of the field, and then have that applied to the pieces as well. So yeah.
All right.
Good observation.
Any more questions? Some ideas presented today seem borrowed from Solid, from Guled.
Solid, is that? I'm not familiar, unfortunately.
You can unmute yourself and explain further, Guled.
Yeah, I mean, I think David knows as well, but like, I don't know, like the single responsibility, but as well as like, you know, like isolating behaviors and not having like a lot of, you know, not adding more props into a component. One of the problems I have when I'm visiting a lot of React components is that each developer touching the file is adding more information. It becomes like a God object, you know, like a component that knows everything. And it's like too smart, you know?
Yeah.
And like, you know, if you have like 10 developers visiting that component during the month, they will add more information to it. And so that's what I was, I don't know, when I was looking at your slides, it seems to be a lot of the ideas, like, I don't know if you know about, what is it called? Like the second one, where, you know, the component should be open for extension, but closed for modification. You know, you should really, yeah.
Sounds interesting. No, I mean, I can understand that because I'm not, what I'm saying is not entirely super new. I'm just giving a different perspective on why is that. Because sometimes I found that, there's a link, thanks. I didn't know if it was a programming style or if it was a different, right, so it's the patterns. If it was maybe a software or something. But yeah, it's just to give kind of further motivation for why to follow certain best practices. Of course, the practices I'm suggesting are very, very popular already, but it kind of helps to have even a new perspective on why those are useful.
Yeah, well, learning a new way to look at something you already understand is always, you know, makes you understand it deeper to a certain degree. Anything else? As I said, we'll put this video up on YouTube. I'll send out all the links. I'll place it on our meetup page as well. So yeah, Jack is here with some further regarding God object. We had prop mania in some of our code base. Our issues was that we had a bunch of components that were well made, but no specified way to compose them. So best guess implementation linked to fragmented behavior. Fix this by using this kind of pattern, including context API.
Cool.
Yeah.
Happy to give you hopefully even more arguments for going in that direction.
Very nice. Okay, everyone. So thank you so much, and yeah, great talk. And I'll see everyone after the summer. Have a good one.
Cool. Thank you.
Bye-bye.
Have a good evening. Bye.